Okay, so intro topic.
Yes.
Sean, mean curvature flow.
I'll still draw some genus too.
Great.
So well, today I'm going to give an introduction to curvature flow. So I'll just tell you what is curvature flow, and then some very basic properties, and then I will specialize in one special kind of solution, which is called Asian solution, and I'll tell you how this is used in the study of curvature flow. Okay, so we start with some manifold inside the Euclidean space, which is n-dimensional inside this Euclidean space for dimension 1 type of surface. Let's assume that this is compact, embedded. Okay, so something like this. So we want to define, we still have the same surface, right? So we want to define the mean curvature, well, we call the definition of the mean curvature vector. So at every point, I consider the tangent plane, and I find some vector v at this point. Then I can calculate what we call the second fundamental form of this embedded surface. So let me write down. It's called the second fundamental form. So basically, you take a curve which represents this tangent vector, and then you take the second derivative of this curve. So I will have a gamma, which is a curve in your surface, which has through the point x, and the derivative of that point represents the vector. Then the second fundamental form is really just the second derivative, but we take the orthogonal direction. Okay, so if you take the tangential direction, that will give you the intrinsic curvature. So this second fundamental form is measuring how it is curved inside the Euclidean space. So we call this sometimes the intrinsic curvature. And h, which is the mean curvature vector, is just the chase of this second fundamental form. So this h is called the mean curvature vector. Some orthogonal basis of your tangent plane. Some orthogonal basis. Okay, just recall the definition. And the mean curvature flow is really just a family of immersions or embeddings which moves along this vector. So this is the abbreviation of the mean curvature flow. So this is just a family of immersion. Which I will use the map F to denote. Well, this is a time derivative. When you take the time, this is the time intervals, and when you take the time derivatives, it's this is exactly the mean curvature vector. Sorry. Okay, so let me just draw some pictures to illustrate what is happening. So the simplest one is the sphere. Let's say of radius 1. And if you calculate the mean curvature vector at any point, you'll see that is actually they're all pointing towards the origin. Okay. Curvature vector at any point, because it's n-dimensional, and I take sum from 1 to n, so it's actually this vector. I'm thinking of this as this point, but also as a vector in the Euclidean space. Okay. So you expect that if you start the mean curvature flow in this sphere, it will just all collapse in a symmetric way, radial symmetric way into a point, and that's exactly the case. So it becomes smaller, and then smaller. Okay, and then after some finite time, it just strings to a point. Okay, so this is one example. And in general, you should keep in, well, the picture that you could put in your mind is something like this. For example, for a curve inside R2, then you see that the mean curvature vector, or in this case, just the curvature vector, is pointing sometimes inside sometimes inside the bounded region, or sometimes it's moving up. So if this is what we have at time 0, then for later time you will expect something like this. So this is what we get. Keep in mind. Okay, so there's several characteristics of very basic characterization of mean curvature flow. So let me just say one. So the mean curvature flow is the gradient flow of the area function of the negative gradient flow. So what does that mean? So for any embedded surface, I can calculate the area. Okay, and I can think of, for example, a family of embedded submanifold, and then I calculate all the areas, and then I take the derivative. Okay, and that if I do that, that's the first variation formula. You'll see the mean curvature vectors showing up in the equation in the derivative. Okay, and so I send this one to the area. Just this one. So if you take the first derivative, the Euler Lagrange equation, that will give you the mean curvature vector. Okay, so you can think of this way: the mean curvature vector is the direction where you will decrease the area in a most rapid way. Okay, so that's one characterization. And another one is the PDE. So let's take a look at the equation, which looks like this one. Okay, and let's say we have a local coordinate. From U to Rn plus 1 with x1 up to xn. This is the coordinate of your manifold. Then you can check that the mean curvature vector is actually the following. So we call Gij to be the dot product of this one. And G upper Ij is just the inverse matrix. Then the mean curvature flow equation. Let me write this thing. So the mean curvature flow equation written in this local coordinate. G upper Ij of the second derivative, and some lower order term. So just and then something that relates to the first derivative of the derivatives. Okay, so you see that this is actually a parabolic equation. So some general theory about parabolic equations should be applicable in the case of mean curvature flow, and we'll see some of them very soon. Okay, and I think I should point out that this Gij depends, of course, on the matrix, and it depends on the first derivative of your function f. Okay, so it looks like it's a very nice equation, but it's actually not, because this one depends on the first derivative. So it's not a fixed Gij. Okay, it depends also on that. So it's a nonlinear equation even in the highest order. Okay, but then you expect some maximum principle that can be used. So I will now give some basic properties about mean curvature flow along this line. The use of PDE. So, for example, we have this avoidance principle. Basically, it says that if you have two embedded surfaces, and then you start the mean curvature flow, if initially they're disjoint, then they will not intersect each other for the later time. Okay, so if two of them are disjoint surface, hypersurface in Rn plus 1, then the mean curvature flow starting at this two will not intersect. One, as long as both of them are still defined. Okay. And the second one is more or less similar to this one. Is that if initially is an embedded surface, and the mean curvature flow stay embedded. This is an application of maximum principle, so or the comparison principle. So think this way. So the sketch of the idea is for both of them. The proof is actually the same picture. So if they actually touch each other, then let's say I have a first time where they really touch. Okay, so those surfaces might look something like this. Okay. This is like time t equals t naught. This is the first time where they touch each other. Okay. Then locally, you can write both hypersurface as a graph. Okay. So locally in this block B, this is M1 at t log, and this is M2 at t log. Okay. So locally, Mi t log inside the form is the graph of the function. And this function U will satisfy a parabolic equation, and it has interior 0. Okay, at this point. Okay, but before this time, they are disjoint, so one of them will be bigger than the other. So let's say the graph is from this direction, and let's say this is U1, this is U2. So U1 at P is always bigger than U2. When T is before the same time where they touch. Okay. But then you're saying that at this time where these two graphs will intersect. But that's not possible by the comparison principle in parabolic equation. Okay. And similar for the same argument, you'll see that if initially you have embedded surface, then it stay embedded. Okay. So another properties which is also very important is that
Can I ask one thing? So can the hypersurface have boundaries?
yes, you can. In that case, well, it depends on how you phrase it. Okay, so you can study the literature problem where the boundary is always fixed. Okay, or you can study situation where the boundary is also moving in some prescribed way. Yeah, and it depends on how you state it. For example, if you fix the boundary, you still have, for example, the maximum principle that they don't touch in the interior. Yeah. So, for example, there's another thing about the literature flow. It is what we call the mean complexity. Well, complexity is easy. It just means that the surface is complex. Okay. Mean complexity means that the mean curvature vector is always pointing to the interior. Okay. This one is pointing. Again, using some maximum principle, you can show that these two properties are preserved. So that means if you start with a convex surface and you start the flow, it will stay convex as long as the flow is defined. Okay. So and it's also by maximum principle. So let me now. Well, I'm just trying to give you a very basic a picture of mean curvature flow. Now I want to consider what we call the singularity model. This is where you cannot use PDE directly. Okay, so well, what does that mean? So one observation using the avoidance principle is the following. So the fact is the following. Okay, so the mean curvature flow, if you start at a compact surface, it's defined only at the finite time. So you don't have a long time existence.
It's always defined a little bit.
Yes, that you always have a short time existence, but you never have long time existence in this. Where if your initial surface is compact. Only the reason is very simple. If you have an initial surface and you start the mean curvature flow of this one, then what you can do is that you can use a bigger sphere to enclose this surface. Okay, such that they don't intersect. Okay, choose a big enough sphere. And then you start the mean curvature flow for both of them. Okay, and the bigger sphere will shrink to a point in finite time. So that's why something must be going wrong in between. Okay, so that means you don't have a long-term system whenever you have a compact inertia. Okay, so how the sphere things in time. So that means, well, if you study only the PDE, probably that's the end of story. Okay, so I have this finite time system. Okay, but in terms of geometry, we want to know what happens if we try to do the flow past the singularity, so to speak. Okay, so so geometrically, what we want is something like this. So the question that we ask is that, is there a way to continue the flow singularity. So let me draw some picture to illustrate what I mean. So that's another situation, examples of a mean curvature flow. So we start with this initial hypersurface. Okay. Which has a thin length in the middle, and these two are sort of bigger compared to this one. Okay, so you can think of this way. So the mean curvature vector is the sum of all the second derivatives, right? So you have this very small sphere here. That means the mean curvature vector is actually pointing towards the interior, at least around this region. And the magnitude will be very big if you choose this leg to be very, very small. Okay, so it goes something. Okay, so if I choose this to be small enough, then you would expect that this leg region will shrink much faster than this two region, and at the end you will get something like this. Okay, this is where t goes to the singular time. This is the picture that we have in mind if we have initial surface that looks like this. Okay, and that's the end of the PDE story. But then geometrically, we want to continue the flows. Okay, and there's several ways we can do it to continue this flow. The first one is I think it's the oldest one. It's called a weak flow. Okay. We will think of all this submanifold as just some subset in the Euclidean space, and essentially, actually, we're thinking of this as a measure, okay, with some extra property, and then we define a flow that is that can be defined on some measure instead of some manifold. Okay, we're not going to talk about that this talk. Okay, the other one is the surgery. Okay, so right before it becomes singular, we cut away the point where we have high curvature, and then we restart the flow. So between these two pictures, there's one picture that looks like this. One thing that we hope to do is that I can cut along this high curvature area, and then I will add two cap to it. And then I'll start the flow right after that. Okay, that's two ways to deal with it. Okay, and I will. Well, the study of Asian solution is very closely related to this surgery procedure. Okay, the reason is the following. So, well, let me just give you some remark. To make this surgery work.
Can I ask one more thing? So I imagine if we cut too early, then I mean the output of the flow that comes after might be different. So how do we decide when to cut?
There's several parameters for us to choose when doing this kind of surgery. Okay, so one characteristic is that if you take all this parabola to positive infinity, they will recover the weak flow. And the weak flow is sort of in some situations. Yeah. So it's arbitrary when you fix a large parameter, but when you take the limits, it's still unique in something. Okay, so well, to make this surgery work, we need to know, need to understand singularity. Understand the formation of singularity. And this is the main study in the area for the past at least 10 years. There's a lot of new results. Okay, so to understand the formation of singularity, just like a minimal surface, we do a blow-up analysis around the point where the curvature is very high. Okay, so we do the blow-up. So let's say I have mean curvature flow. Where is defined, this is the maximum existent time, capital T. Okay, and then it becomes a singular such that the mean curvature, the norm of the second fundamental form goes to infinity as equals to this capital time. Okay, so it goes to, well, the curvature becomes advanced somewhere. Okay, I want to blow up around the area. Okay, so let's say around some capital X inside the ambient space. This is the capital X that we have in mind. Okay, so we do a blow-up analysis. So first we translate everything to this point, to the capital time, and then we scale it. Okay, so we'll consider this parabolic scaling. Because this is a parabolic equation. So it goes like this. So I will have this sequence of scaling parameter, which goes to positive infinity. Okay. And we define a sequence of mean curvature flow. So we do a translation, space-time translation, and parabolic scaling. So let's give them like this one. It's not okay. So besides this scaling parameter, we have also a sequence of points which tends to the singular point. Okay, and then we do something. Okay, so we scale the space parameter with lambda, but the time parameter we have to scale in lambda squared. That's the scaling invariance for the heat equation. Okay, and if we do this kind of scaling, this is still a mean curvature flow. Okay, still a mean curvature flow, and that means we have a sequence of mean curvature flow, and we want to take the limit. Okay. I might or might not be able to take the limits, but let's say if I have a subsequence which converge, then I will call this a limit flow. Any subsequential sequence of these FIs or limit flow. And I want to point out that this is where we have what we call the Asian solution. I haven't defined what that yet. Okay, so the limit flow, let me just give a name for it. So it's going to be S of T. Okay, but think this way. So this numbers tends to infinity. Okay, so the flow at the limits actually start from negative to infinity. Okay, so that's what we mean by Asian flow. It comes from negative infinity. So this T is negative infinity to 0. So this is what we call an Asian flow.
Another 16 minutes.
16. Oh, okay. Okay. That's fine. Okay. So well, I hope I'll be able to draw some pictures soon. So this is what we mean by Asian solution. That is defined from negative infinity. Okay, so and it comes from this Blowup losses. So if you do the parabolic rescaling around the singular points, you naturally, if you have a limit, then that limit naturally is an Asian solution. Okay. So as a special case about this this procedure. So in here, I choose the sequence which tends to the same to the capital X, right? But in some special case, I can fix this sequence. Okay, I'm just blowing up around the fixed point. Okay, this is x1, this is x1. Then we can say something about the limits actually. This is done by Houston in 1989. And then in Manon several years later in a more measure theoretic setting. So in a case where this point is fixed, okay, there's actually subsequential limits. Okay, so this Fi subsequence is Fi. If this point is fixed, okay, converges to a self-strengthening solution. Well, what do you mean by self-shrinking? For example, the sphere is an example of self-shrinking solution. So it stays the same shape, okay, in a mean curvature flow. Okay, just that it becomes smaller and smaller. Okay, so by self-shrinking, that means, for example, the sphere, okay, will be one of the self-shrinking solution. If you think of this as a family of sphere, starting from negative infinity and then all the way to the center. That's one example. And then also I can take product with any real line. So this is also a self-shrinking solution cylinder. Okay, a cylinder is just the standard cylinder. Okay. So the main curvature vector is always pointing towards this center axis at every point. Okay. So if you start the main curvature flow, this is the MCF. If you start that, then it becomes thinner and thinner. Okay, and then at the singular point, it becomes a straight line. Okay, and I can think of this. Well, although every point is just moving along this direction, this is not the case that this point will move to here, right? But I can think of this whole picture as a self-shrinking solution. So you can just scale. You can recover this cylinder by this one by multiplying the fixed number. Okay, so this point might be sent to some point here. Okay, but it doesn't matter. The total shape is given in a shrinking way by a rescaling constant. Okay, so this is what we call the self-shrinking solution. And I think I can draw some picture about this self-shrinking solution. Just to give you some examples.
What about this ancient flow? What's an example of it?
This self-shrinking solution will be one example. Yeah, because the sphere can become, it comes from, what should I say? I can scale it. I can scale it to be as large as possible. Right? So yeah. So let me just give you some examples of self-shrinking solution. Well, the sphere. This is the case when n equals 1. Okay. The sphere is a self-shrinking solution. Okay. Actually, in the case of n equals 1, it's completely classified. You can actually find all the self-shrinking compact solution. Okay, and it's called the average random curve. So they're all convex in the sense that the curvature is positive. So some examples like this. So in convex, in the sense that the mean curvature vector is always pointing in one direction, okay, and it's just straight out to a point, just like this here.
That be a Blowup logo?
Sorry.
Shadeless number is.
Yeah, right. Oh my God.
Okay, so you can think of this something as a simpler kind of function solution, probably the simplest one, and it shows up in a very special way of blowing up the singularity. But in order to understand the singularity, we actually need to understand all the a lot of different solutions, not only this one self. Okay.
Should we think of types of singularities as types of what happens if you find some like
I would think of this as a way to parameterize the shape of the around the singular time. Okay, so let me draw a picture to illustrate what's happening. So going back to this blow-up procedure in this picture. Okay, so I'll draw like two similar pictures of this form. So at some points, the leg becomes thinner and thinner. And then when t goes to capital T, it becomes a single. Okay. So I can do a blow up at this point, okay, exactly at this point, this capital X, okay, and it will become something like this because I'm taking this lambda I to positive infinity. So at the end, I don't see this two sides anymore. I can see only what is happening here. So it becomes something like this. So, but then when you take I goes to infinity, then you see it's actually a cylinder. It's a self-shrinking cylinder in this case. Okay. I want to point out that I think that's one nice picture which illustrates why fixing one point is not good enough. Okay, so there's another similar picture to this one. Okay, this is called that picture. And there's some parameters. So I can choose this to be bigger and this to be smaller, so on and so forth, right? But that's a degenerate critical one, which shows you why we have to study all the Asian solutions. So in this picture, it shows as if that the shrinking here is faster than the shrinking of this sphere, right? The thing is, I can choose this to be smaller and smaller, and eventually I can choose one critical one, such that this leg pinch collapse, and at the same time this ball collapse. Okay, they both collapse at the same time. So the picture is still something similar. Okay. But then this is smaller. Okay, and when you take t to the critical time, so it becomes something like this. And then at the singular time, this left hinge collapse, and together the ball also collapse. So it becomes something like this. Okay. So why do I want to point out this situation?
Why could that actually happen?
That happens when I choose the radius of this ball to be smaller and smaller. So you can think it this way. So if this ball is extremely small, okay, then maybe there's no singularity here at all, right? So it just goes away. It becomes rounder and rounder. Okay, the left hinge is not obvious enough. Okay.
It seems a little bit unstable. Sometimes it does one thing.
Yes. This is the case where a small interpretation will avoid that singularity. Okay, so it's an unstable situation. Okay, but there's a critical one in between. Okay, that exactly this one happens. Okay, the ball together with the leg collapse at the same time. Okay, and you can think this way, because this ball is so small, the curvature is very big. Okay, and you can think it this way, because and it turns out that the curvature at this ball is actually much bigger than the curvature at the leg. Okay, because on the leg there's only one direction, but on the ball there's two directions, right? So the curvature here is actually much bigger. Okay, so this is in this picture, in this degenerate situation, this is the worst point. Okay, and you want to know what is happening at this point more than this left hinge. Okay, so this is in this situation, we need to choose the center of the scaling to be moving in order to know what is happening here. Okay, and it turns out that if you do that, you don't get the cylinder anymore. If you fix the capital X here and do the scaling, you have the cylinder. But if you choose this point to be moving, you get something completely different actually. So it becomes what we call the full solution. Okay, this is another weird mean curvature flow where the shape is not changing, but it's moving along one direction. It's what we call translating solid. The idea is that if we are able to understand all possible limit flow at around a singularity, then we can recover the information about that singularity. Okay, so that makes the classification of Asian solutions sort of important, and it's a very intense study for the past several years. Okay, so how many times? Oh, 1 minute. Okay. 1 minute. Oh, hang on, just stop.
Thank you very much for this beautiful lecture and lots of nice pictures. We have time for a couple of questions. If yes.
We have got the degenerate situation. That's the sphere collapse at the next.
Can you say that again? The sphere
We
what?
have the degenerate next. The sphere collapse also at the next or at some other.
Yes, they're exactly at the same point. Yeah. This small ball converge to this point, and the left hinge happens also at this point.
So you can all have it. It goes out. So you like this drawing, you have two different points.
You mean this xi?
Yeah.
This xi is the blow up parameter that I choose. I have to choose this. I have to blow around this point instead of this fixed electrical point. But this xi will converge to this x eventually.
And what I really mean is that you can have this situation where, say, the sphere collapse at the nearby point close to the next, but not the next.
Yes, but in that case, they might not become similar at the same time, right?
I know where not.
They might or might not become similar at the same time.
I think there was about 3 questions. One more. it's close to being. Yeah. 1 o'clock. Thank you everyone for coming. We are speaking here maybe in 2 weeks or something like that.